Welcome to this comprehensive guide on heat exchangers and heat interchangers, presented by Professor Dr. Santosh Kumar Singh. In this presentation, we will explore the various types of heat transfer devices, their effectiveness, and their applications across different industries. A heat exchanger is a specialized device that transfers thermal energy between two or more fluids without allowing them to mix or come into direct contact. These devices are crucial in numerous industrial applications, including power generation plants, chemical and petrochemical industries, HVAC systems for climate control, refrigeration units, cooling systems, and food processing facilities. The fundamental purpose of any heat exchanger is to transfer heat between fluids. This is achieved by facilitating heat transfer from one fluid to another while keeping them physically separated by a solid barrier. This separation ensures efficient heat exchange without mixing the fluids. Heat exchangers come in various types, each with unique designs and applications. Shell and tube exchangers are the most common, featuring tubes inside a cylindrical shell. Plate-type exchangers use metal plates for heat transfer between fluids. Finned tube exchangers have extended surfaces to enhance heat transfer. Air-cooled exchangers use ambient air to cool fluids, ideal for areas with water scarcity. Spiral and corrugated exchangers feature spirally wound coils for increased turbulence and heat transfer efficiency. Fins are used in heat exchangers to increase the surface area available for heat transfer, thereby improving the overall heat transfer rate. They are particularly beneficial when one fluid has a lower heat transfer coefficient compared to the other, such as air or gas. By extending the surface area, fins compensate for poor heat transfer characteristics and enhance efficiency without significantly increasing the overall size of the exchanger. In a shell and tube heat exchanger, the fluid with higher temperature typically flows through the tubes. This arrangement protects the shell from excessive heat and reduces overall heat loss to the surroundings. It also simplifies design calculations and makes maintenance easier. Heat exchanger effectiveness is a dimensionless parameter that measures how close a real heat exchanger comes to achieving the theoretical maximum heat transfer rate under given conditions. It is determined by factors such as the number of transfer units, heat capacity ratio of the fluids, and the flow arrangement. Effectiveness is crucial for design and comparison purposes. The effectiveness of a heat exchanger is defined as the ratio of actual heat transfer to the maximum possible heat transfer. This formula is a critical parameter in heat exchanger design, helping engineers assess how efficiently a heat exchanger operates compared to its theoretical potential. LMTD, or logarithmic mean temperature difference, is a logarithmic average of the temperature difference between the hot and cold fluids at each end of a heat exchanger. It is used in the fundamental heat transfer equation to calculate the overall heat transfer rate, considering the temperature differences at the inlet and outlet. When deriving LMTD for heat exchanger calculations, certain assumptions must be made for the mathematical model to be valid. These include steady-state conditions where flow rates, inlet temperatures, and other parameters remain constant over time. It's important to note that flow conditions are unsteady, which can affect the accuracy of LMTD calculations. Parallel flow and counter-flow heat exchangers have distinct design trade-offs. While both share common traits, counter-flow arrangements generally provide better heat transfer efficiency due to a more uniform temperature difference throughout the exchanger. This maximizes the mean temperature difference and results in higher efficiency compared to parallel flow arrangements. Counter-flow arrangements maintain a more uniform temperature difference throughout the exchanger, which maximizes the mean temperature difference and results in higher heat transfer efficiency compared to other flow arrangements. This makes counter-flow a preferred choice for achieving optimal heat transfer. Designing a heat exchanger involves several practical considerations. Material selection is crucial, with factors like thermal conductivity, operating temperature, and chemical compatibility playing a role. Fouling and corrosion must be accounted for, as they can affect performance. Maintenance access and operating limits, such as pressure and temperature constraints, are also important for ensuring efficient and reliable operation. Air is usually passed on the shell side with fins in heat exchangers because it contains impurities that can clog tubes. By passing air on the shell side, the risk of blockage is reduced, and the fins help compensate for air's poor heat transfer properties. This arrangement also makes maintenance and cleaning more manageable. In summary, heat exchangers come in various types, each serving specific applications and operating conditions. Key considerations in their design include material selection, fouling resistance, maintenance access, and operating limits. Performance metrics like LMTD and effectiveness are crucial for evaluating and comparing designs. Counterflow arrangements generally provide better efficiency compared to parallel flow, offering more favorable temperature profiles. Thank you for your attention.